Hello everyone, I'm Taha Tekdogan, and I'm here to present our paper, gSuite, a flexible and framework-independent benchmark suite for graph neural network inference on GPUs. I'm sorry that I'm not able to participate at the conference in person, but I'm going to do my best to express myself through a recorded video representation. Here in this work, we propose our novel benchmark suite, which we call gSuite, for graph neural network at inference level on GPUs. The outline of this presentation is much like the organization of our paper. I start by giving some background and introductory information about graphs and GNNs. Then I will be talking about limitations of state-of-the-art. After that, I'm going to introduce our design approach, and then tell how we evaluate the performance of GNNs on our benchmark suite by comparing with other frameworks. Finally, I will deliver our results, related work, and conclusion. But first of all, I'd like to mention why graphs. Graphs are able to express the non-Euclidean data. Just as a quick reminder, in Euclidean data, the connectivity information of nodes are static and same for all nodes, just like in pixels. On the other hand, for non-Euclidean data, this connectivity is dynamic and can change greatly from node to node. Graphs are able to express the relationship among objects and the topology of such networks. We can give some examples to graphs such as molecular structures, social networks, and transportation maps. I put here the illustration of Istanbul subway network, which is kind of huge and complex. And why graph neural networks? Recently, learning tasks have been so charming that we can easily see them in action in many areas. Graph neural networks are deep learning-based methods that enable us to operate such learning tasks on graph-structured data. GNNs are able to operate many tasks, including node prediction, link prediction, and graph-level classification. Here you can see an example for a GNN pipeline with two hidden layers. As you can see, there are also activation layers after each hidden layer, which is rectified linear unit for, or really for short in this case. Before diving deeper, let's clarify some concepts, definitions, and notation. A graph is represented with G and defined with two sets, nodes V and edges E. Nodes are connected to each other with edges. We can also represent the number of nodes and edges with symbols N and M respectively. In more GNN-related definitions, we first need to define the layer number. As you may recall the previous schema, our GNN pipelines consist of many layers, including input layers, hidden layers, and an output layer. These layers represent the GNN model's gradual evolution through the pipeline, and they are sequential. At each layer, our nodes and edges may contain information as latent vectors. Such information tells us about the corresponding nodes or edges properties, which we call representation or embedding. We can also represent the neighborhood nodes of a node V as NV, where these nodes are directly connected to node V. Let's talk about the computation of GNNs. A typical GNN consists of two stages, inference and training. Inference is applying model coefficients to current graph features. Training is updating the model coefficients analogous to learning method. We, in this study, specifically focus on the inference phase of GNNs. The inference part consists of two consecutive phases, aggregation, or message in some studies, and combination, or update in some studies. Aggregation refers to capturing information from a node's neighborhood nodes and accumulating them into its feature representation. Combination, on the other hand, refers to updating a node's representation by using the output of aggregation phase, which is mostly a multilayer perceptron, or MLP for short. There are plenty of frameworks to build and run a GNN pipeline. The most popular of these frameworks are PyTorch Geometric and DGL, where we imitate their implementations during the design of our core kernels by purifying them from PyTorch or other framework dependencies. On the other hand, there have been many types of GNN models proposed during the last decade. Each model has a specific formula for aggregating and combining the node features. There are a myriad of benchmarking and characterization efforts on GNNs. Here we take some frameworks, characterization studies, and benchmarks into consideration, and compare them in terms of some features. We observe that these studies contain a dependency to other frameworks and libraries, which complicates the performance evaluation. These works also push researchers to interfere with their code base. Our study, on the other hand, can build any desired GNN pipeline by just passing a few parameters to the program. gSuite also does not have a dependency to any other frameworks or libraries, and currently includes 3 GNN models and 5 graph datasets. While designing the gSuite, we took 3 key features into consideration: flexibility, extendability, and independence. gSuite is flexible to allow building GNN pipelines by selecting the desired dataset, GNN model, number of layers, computational model, and framework, using either gSuite's core kernels or other frameworks implementations. gSuite is extendable because it allows researchers and engineers to extend the suite in any direction. By utilizing MP and SPMM core kernels, a new GNN model can be built in a plug-and-play manner. gSuite's core kernels do not have any dependency on any GNN or DNN frameworks. However, we still give a choice to the end user for alternating between a GNN framework, like PyTorch Geometric or DGL, and our GNN implementations. Core kernels are the most primitive building blocks for GNN computation. We implemented these 4 core kernels with CUDA and used them for building the GNN models, analogous to their formula. Here you can see there are 2 types of computational models for GNN computation: message passing, or MP for short, and sparse matrix multiplication, or generalized matrix multiplication. We can use SPMM for short. The characteristics of these computational models have an important effect on the characteristics of GNN computation. We are going to imply them in the results section. To illustrate our simple and GNN-oriented approach, I put here the computation schemas of MP and SPMM GCN model. While orange boxes represent core kernels, yellow ones represent data. This is the software architecture of the gSuite from a high-level perspective. All the end user has to do is passing a few parameters, such as number of layers, datasets, GNN model, and etc. The user interface interprets these parameters. Datasets are loaded, and the intended part of the codes are run. In our experiments, we included 3 popular GNN models: GCN, Gene, and GraphSage. Our implementations are two-sided, which means we implemented both MP and SPMM versions of the GNN models. And we also ran the experiments with these 5 datasets, where each of them represent a unique behavior in computation because of their number of nodes, number of edges, and feature length. Experiments are ran on NVIDIA Tesla V100 GPU. NVIDIA's NVProf is used as a hardware profiler, and GPGPU Sim is used as a cycle-accurate simulator. We use some evaluation metrics to measure the performance of GNN models with various datasets using gSuite. These metrics are execution time, instruction breakdown, issue stall distribution, warp occupancy distribution, L1 L2 cache hit rate, and compute memory utilization. Our first metric is end-to-end wall clock execution time. In general, execution times of PyTorch geometric is longer than other frameworks. This is mainly because of the initializations that are performed as part of their implementation. Since gSuite eliminates high-level library dependencies, its implementations tend to run faster than other frameworks in terms of end-to-end execution time. On the other hand, we analyze the distribution of kernels in terms of execution time. gSuite shows a similar distribution to that of PyTorch geometric and DGL. We observed that the GNN model is the main determinative factor for the distribution of kernel execution times. We collected the instruction breakdown information from MVPro for each kernel by adjusting the GNN model and dataset during the experiments. We observed that the instruction breakdown of the kernels are showing characteristic behavior and not object to change as GNN model or dataset is adjusted. Issue stalls explain why an active warp was not eligible during its execution. In our experiments, it varies greatly as we adjust the dataset and GNN model. As the size of the dataset gets larger, all the core kernels except SGEM develop memory dependency. We found that the memory dependency is a dominant stall in both MP and SPMM-based implementations, with 46% on average. This is due to irregular memory access pattern of GNN inference tasks. From the GP-GPU sim, we used metric warp occupancy to show warp distribution of the kernels. This metric stands for the ratio of active warps to maximum number of supported active warps. Here you can see the distribution of warp occupancy for MP-based implementations on different GNN models and varying datasets. During the experiments, we observed that the type of the GNN model plays a crucial role in pipeline utilization. MP-based kernels such as scatter and index select of GCN model tend to stay idle during the execution, unlike that of GIN and SAGE model. However, the GEM kernel is immune to these GNN model adjustments. We compared L1 and L2 cache hit ratio statistics taken from MVProf and GP-GPU sim. We observed that L1 cache hit ratio values for profiler and simulator are more aligned than L2 cache hit ratio values. Specifically, for some workloads such as Cora and Sightseer, the simulator indicated memory performance is not well matching with the hardware-based memory performance. This shows us that more validation study is required on GP-GPU sim's memory model. From our detailed analysis on L1 and L2 cache hits, we observed that the GCN workloads have some or limited locality. This suggests that architects should study GNN-friendly caching and prefetching options. Specifically, index select kernel cannot utilize memory efficiently. Memory utilization level combined with the high L1D cache miss rates we observed, we suggest researchers to investigate other caching techniques to be applied particularly on index select kernel. We also noticed that larger input workloads result in less L1 and L2 cache hit ratios. These extremely low L1D cache hit rates points out that caching may not be a good technique for GNN inference. Therefore, using L1 cache bypassing techniques can be considered as an alternative to alleviate such problem. We also compared the compute and memory utilization of kernels. We observed that scatter kernel utilizes memory more efficiently than other kernels, especially when employed in GIN and SAGE models. Compute and memory utilization of SGEM kernel scales up as the input workload is bigger. For example, with live journal dataset. As conclusion, we propose a framework-independent and flexible benchmark suite for graph neural networks at inference level. We make architectural implications on GNN computation and make suggestions based on our findings. Furthermore, our work gSuite is open source. We welcome any suggestions and contribution to our benchmark suite. You can reach to gSuite by using these QR codes and links below. As a future work, we plan to enhance our support for GNN training by implementing the training-related functions in gSuite. We also plan to support different architectures such as FPGAs and AMD GPU cards by implementing our core kernels with OpenCL. I would like to genuinely thank to my advisor Ayşe Yılmazer for guiding and supporting me during the process. And I also would like to thank to Aselsan for compensating the expenditures. Thank you for listening. You can reach me through my email and you can add me on LinkedIn. I will be more than happy to be in touch with architecture and GNN community. Thank you.